Assalamu alaikum. In the previous lecture, we have discussed about modeling of desertification. So we started with the definition of modeling, and then we went through the modeling types and all the model types, and finally we went through the modeling processes. Today, we're gonna have another interesting lecture that build up on the modeling of desertification. It's gonna be very short. So the outline of today's lecture, we're gonna start with the biophysical modeling, and then we're gonna go through different types of biophysical modeling, specifically climate models, land surface atmosphere exchange models, vegetation models, and finally erosion and hydrological models. So without further delay, if we're gonna go back to the definition of desertification, we're gonna see that desertification is a land degradation that is caused due to climate changes and human activities. And the human activities are basically in the environmental aspect, socioeconomics, and political aspects. So biophysical model is basically a model that helps us to model desertification, or at least some of the factors that basically contribute to desertification. Because in a biophysical model, it's basically a simulation and a modeling of a biological system. And basically in this type of models, you are trying to model the physical properties of that models, and then you can predict the influence of the biological and the physical activities on the system itself. Biophysical modeling includes different types of things, but in this lecture we're gonna go through the climate models, land surface atmosphere exchange models, vegetation models, and erosion and hydrological models. So all of these four types of models basically are different. They are considered as different examples of the biophysical modeling. So let's start understanding each one of them. One of the most important factors that can lead to desertification is basically climate change. But how can we model climate change, and how can we understand whether these changes in the climate are caused by human or by nature, or it's basically a combination of both? So climate models can help us to do that. In climate models, you are basically trying to collect data, and from these data, from the past data of the climate, and with the recent data, you would be able to analyze what happens in the past and the present, and from that on you build on your models. And once your model is reliable, you can then have future scenarios, and you can see whether these changes of how these changes on the climate can affect the ecosystem, and specifically can cause desertification, as an example. So a climate model is basically a numerical models. So in climate models, they are basically running as supercomputers that really required, because you put a lot of data, and from these data you use a supercomputer, powerful computers that can analyze these data and simulate, and then they can predict the future. So these numerical models basically try to see or study the interaction and model the interaction between the climate factors like the atmosphere, ocean, land surface, and ice. And once you put all of these, your climate model can help us to understand, for example, whether these changes in the climate are caused by human activities, or caused by, or happened naturally, or happens by a combination of these. And when you understand basically the past, the present, and the future climate, it will help you to understand how the ecosystem functions. So you would know that, well, this is a normal situation, a climate situation. For example, it's normally to have a temperature ranging from 20 to 40 in Oman, and you have it like in the summer in this range and in the winter in this range. So this is, you would see that this is a normal situation. But any times that you find out that the temperature exceeded the normal situation, like if the temperature goes beyond, let's say 50, and then it stayed for months like that in Oman, then you would know that, wow, this is something abnormal. It doesn't happen before, it didn't happen before. So this is something unnatural, and then you might attribute it to climate change, for example. But how can you do that? It's basically by the climate models. And once you predict the climate changes, and once you're familiar with how the ecosystem function, then you would be able by these models to test different management scenarios that can try to reduce the effect of climate change, and that would help the decision makers to also to prioritize and to make these critical decision makings. One of the famous climate models is called the global climate models. So basically, in a global climate model, you are trying to study again, or you're trying to model the climate in a global wise. So you are taking in consideration all the earth, like what you can see in these pictures, and you would be able later on to predict the changes over a long time. Again, one very important thing to emphasize here, that the quality of your prediction is basically determined by the quality of your data. So the more precise the data that you have from the past and the present, the more reliable your model will be. Because remember, for modeling, data is very important. Once you have that accurate data, then you would be able to have an accurate prediction. Now let's move to the second type of biophysics. If you want to understand and model the interactions between soil, vegetation, and the atmosphere, then land surface atmosphere exchange is one of the best models. And one of the examples of this type of model called Soil-Vegetation-Atmosphere transfer. So you know that there are actually water can be lost from the soil and also from the vegetation, and the vegetation and the soil respond differently to different climatic conditions. And this is very important because it determines how susceptible the land to be for example, to climatic conditions, or for example to drought as an example, and that would affect the survival of plants, and then it would affect the susceptibility of the land to be affected by other factors like the rain and so on, and then erosion, and then it can lead to desertification and so on. So basically, in soil vegetation atmosphere transfer model, you are trying to model the impact of the atmospheric inputs, like what you see in the picture here: net radiation, air temperature, air humidity, wind velocity, and precipitation. You're trying to model the impact of these inputs on the soil and the surface condition. And then you're going to see how heat, for example, transfer from the soil in the plant to the atmosphere, and vice versa. I mean, from the atmosphere to the plant and to the surface. And that again would affect for example, the evaporation of water, would affect the temperature in the soil, and you know that the temperature of the soil can affect, for example, the roots and so many other factors. So by doing these models, you would be able to understand, for example, the surface processes, or the processes that happens on the surface. And you're gonna also understand how, for example, individual plant or individual plant species can respond to different climatic condition, and how all the plants collectively would also be influenced by these environmental changes. For example, you look at the forest, how the forest as an ecosystem with different plant species with different sizes and so on can respond to climate, and how the things, or like the heat and water, can be exchanged and so on. And basically, once you get all of this information, you can use it in the hydrological balance, in the hydrologic cycle. That's why this type of model is really important, and also the results of this model can assess or is also useful to climate change models. So you can use some of the results of this model to be useful for the climate change modeling. If we come to discuss how the land would be susceptible to erosion, for example, and how can it be stable, then vegetation is one of the most important factor. And that's why we have also to model the vegetation. And one of the indicators for us to see whether we have a desertification or not is also to look at the vegetation cover. So if we have a significant reduction in the vegetation cover that is not reversible and not recoverable, then we know that we have a land degradation, we have desertification. And that's why we have to model the vegetation. So vegetation model basically try to model the vegetation cover, because you know that vegetation are very important for the atmosphere and the soil and the surface. And you know that if you have a change in the climate, then it would affect the vegetation cover, because the temperature or the climate condition might not be suitable for that particular plant species, and then it will extend. Other than that, for example, the rainfall or the amount of water in the soil might not be enough, and then you have drought, and then vegetation dies, and so on. And once your vegetation cover is gone, then even a small rainfall amount can cause significant erosion, and that would further degrade the land as we saw. And not only that, the vegetation itself can affect the climate, because you know that one of the most important components to climate and climate change is the carbon dioxide, and vegetation can help us to sequester and absorb that carbon dioxide and turn it again into oxygen. So once you lose the vegetation cover, you would affect the balance between carbon and oxygen cycle, and that would affect the climate change, or would cause a climate change. And one of the examples of vegetation models is called dynamic global vegetation. Now the last part of this lecture is erosion and hydrological models. And because you know that as water flows on the surface, it carries with it sediment, and it can erode the soil. And once the soil is eroded, like forming gullies and rills as you see in this picture, then the next time as water flows on the surface, it would flow even different than the previous time. It might flow rapidly, because now you have created these conditions that allow or increase the speed of water over the surface. And once you get erosion, then you are further degraded your soil. One of the most important models that can be used to model erosion is called the universal soil loss equation. And to give you a brief idea about universal soil loss equation, is basically an empirical model. Again, what is empirical models? That has been developed from data. That's why one of its advantage is that it is a symbol, but one of its disadvantage that it is an empirical model, so it means it cannot be applied everywhere. It has to be applied to a condition that is similar to the data where it has been driven. And as you see that the universal soil loss equation consists of the following, as you see here down. So it is A equal to R times K times LS times C times P. So A stands for average annual soil loss. So this model calculates for you how much the soil lose, like in ton per hectare per year from a land, and it combined the factors or the effect of rainfall, effect of soil, and the effect of slope, and the effect of the management. So R stands for rainfall erosivity factors, which means that if you have, for example, more erosive rain, like higher, like very intense rain, then that intense rain would cause more erosion than a mild rain, a calm rain. Then the soil erodibility factors describe how the soil is susceptible to erosion, or how easy or difficult the soil can be eroded. So again, different soil types responds to erosion differently. If you have, for example, sandy and silty clay, then they will be easily eroded compared to a clay soil. So again, sand and silty soil can be more eroded than a clay soil, because clay soil is more cohesive, while sand and silt soil are loose, so it can be easily eroded. The other factor is the LS, the slope. So if you have steeper slope, then you know that water would move faster, and therefore it can erode more sediments. And if you have also a longer slope, then that have a different effect than having a smaller slope, because in a longer slope you would carry even more and more sediments. Then we go to the land cover management. If your soil having a vegetation, then that is different than bare soil, because when you have a vegetation, then you are protecting your soil and stabilizing the soil compared to have a bare soil. And then the conservation practice, which describe how you are trying to manage the soil erosion. For example, if you are making terraces, then you are reducing the slope, and that as a management would eventually lead to a lower soil erosion. Or for example, if you are trying to reduce the slope by any mean, or having, for example, contours or growing vegetation or different type of vegetation. So by this model, you can again study the interaction of water, the soil cover, and the vegetation and the management. And that's why it is also a very important types of models that can help identification. I got you this one, so you can do this modeling in online. So there is a web page, as I posted here, and you can put all of the factors, and then it can calculate for you how much the soil loss will be from the soil cover, so on. So that's all for this lecture. I hope you enjoyed it, and see you in the discussion session. So you can go through the references. It's from chapter 6, and also you can watch the videos that I put the links there in each slide. So thank you and take care. Bye.